Okay, now I'm recording. Okay, great. Okay, that's hilarious. Okay, thank you, Sophia. Sophia, you can't go anywhere. You just have to keep on staying. Okay, all right. So guys, I was going to begin by going over questions. In class, I was going to go over questions. So first of all, tell me what questions that you guys have. I haven't talked anything about optimization. So if we could go to your optimization worksheet and throw some questions at me from that. Let's start there.
Could you do number 13 on the optimization sheet?
Yes. So let's take a look at 13. Ooh, that's a good one. Okay. All right, so I'm going to switch to my hover cam here if I can. It's been a while since I've done this. Okay. Oh, well, that's not working, is it? Let's try that again. Okay, there it is. Okay. All right, so this is 13. Hopefully you guys can see it. It says a cylindrical metal container open at the top is to have a capacity, so that's volume, of 24 pi cubic inches. So that's our volume of the can or the cylinder. The cost of material used for the bottom of the can is 15 cents per square inch, and the cost of the material of the curved side is 5 cents per square inch, okay? So we have the cylinder, and it says that it's open at the top, so we can go inside. We don't have to pay for the top, in other words. We're only paying for the bottom and the sides. All right, so let's see. We've got some costs, and we want to, in part A, we want to minimize the cost of the material, which makes sense. If you were a manufacturer, you would want to minimize your cost. So what would be the dimensions so that I can minimize my cost? Anyway, okay, so I'm going to write an equation for cost. I always start off by writing the equation for what I am trying to either maximize or minimize. So always start off by writing that equation. So this is going to cost 15 cents per square inch of the base and 5 cents per square inch of the curved side. So I'm going to start off with this 15 cents. 15 cents times, and here I want the area of the base because it's this per square inch, so it's area of the bottom, which is our base. And then we're going to add to that 5 cents times the area of that portion, the curved side. Okay, so in general, that's how I set up any cost equation. So this is going to be the area of the base. Well, the base of the cylinder is a circle. So this is just going to be pi r squared. And then the area of the curved side, remember if we take this cylinder and we slice it down the side and then we spread it out, it would be a rectangle. And the rectangle would have a length and a width. It would have a height, we'll call it h, and then the width of it would be the circumference of this base, right? So the length of it would be the circumference, which I need you to know is 2 pi r. That's our circumference. So the length times the width would be the circumference times the height there. So that's how I set that up. That's my cost equation. And now I want to get the cost equation with only one variable over here. Either R's or H's. So it's going to be easier for me to get rid of that H. So I need to change H, and it'll have something with R's in it. And the way we change H is we're going to use this volume. We know that the volume, our can has to have a capacity of 24 pi. So I'm going to come over to the side. I would give you the volume. I don't know why I didn't in this worksheet. Usually I try to make my worksheets as you would see it on a test. But I would give you that the volume of a cylinder is pi r squared h. I would give you that, okay? So I'm going to use that. And so I know that 24 pi is going to be pi r squared h. I can solve this for h by dividing both sides by the pi r squared. And the pi's will cancel out, and h will be 24 over r squared. So I'm going to replace that h with 24 over r squared. So I'll have c is equal to 0.15 pi r squared plus, I'm going to go ahead and multiply 0.05 times 2, and that'll be 0.1. And then I'm replacing h with 24 over r squared. So I'm still simplifying. I keep on simplifying until I'm ready to take a derivative, okay? Keep on simplifying until you're ready to take that derivative. Plus, I'm gonna go ahead and multiply 24 times the 0.1, that'll be 2.4. So it'll be 2.4 pi divided by r, okay? So this is my new cost equation. So I always take a look at my equation and I ask myself, do I know what this graph looks like? And when I look at this, I don't know what the graph looks like. I love it when I ask myself that question, what does the graph look like? And my answer is, oh, it's a parabola, you know, whether it's upside down or right side up. If it's a parabola, then I can see the minimum, or I can see the maximum. I can see it if it's one of these. If it's a cubic, then I can imagine, oh, I can see that, right? Or I can see this max or that min. If I can see it, I like it. Here, I don't know what the graph of that looks like. So that just means I need to check to make sure I know what's going on at the end. When I'm always going to take the derivative. I'm going to set the derivative equal to 0. And then I need to consider my endpoints and what's going on, okay? So it's time to take a derivative here. When we take this derivative, this is just going to be the power rule. So 2 times 0.15 is 0.3, right? So that'll be 0.3 pi. Reduce your power on your r by 1. And now the derivative of this. So the derivative, remember, the derivative of 1 over x, that's one that I kind of want you to just know. It's negative 1 over x squared, okay? If you don't, you know, if I don't think of it that way, then I need to think of this as x to the negative 1 and use the power rule on it. So that's a good one to know. So I know I'm going to change the sign, leave the top, and we're actually reducing the power by 1, but since it's on the bottom, it's going to look like it's increasing by 1. Okay, so now I'm going to set this equal to 0. So I'm setting this equal to 0 because, again, I'm finding these relative maxes and mins here. And now we have to solve this for r. So it's a rational equation. This was our one calculus step. Now the rest is going to be algebra. So I'm solving this rational equation. So think back to all the times you solved a rational equation. We're going to multiply both sides by r squared, which is legal. So I'm multiplying both sides by r squared, and I'm going to have 0.3 pi r cubed minus, and then these r squareds will cancel, 2.4 pi is equal to 0. Come over to the side. And solving for r, I'm going to have r cubed is equal to, so I'm bringing the 2.4 pi to the right, dividing by 0.3 pi. So I'm going to have r cubed is 2.4 divided by 0.3. Think of that. That's the same. If you multiply top and bottom by 10, which is legal, if you multiply both top and bottom by 10, we get something a lot better to look at, right? So this is just 8. So I get r is 2. Okay. So I get this r is 2, and my question is, how do I know that that's a minimum? How do I know that's a minimum and not a maximum for some reason? Well, to tell, we would kind of need to do a closed interval, or let's take a look at, to be totally certain, we would do a closed interval test. What's the lowest that r could possibly be, you guys? What's the lowest r could be? Do you agree, 0? Lowest it could be is 0. And the highest it could be, there, I'm sure there is a high because the volume can only be 24, but I don't really care. We'll just, I know that there is a maximum it could be, but let's just not go there right now. I'm going to just do a little sign chart. So I'm looking at C prime here. So I'm putting, because remember the 2 came from C prime, so I'm doing it on C prime. If I put a 1 back here, if I put a 1 in for R, I'm going to have 0.3 pi minus 2.4 pi. That's going to be negative. So I'm going to have a negative there. If I put a very, very large number in, I'm going to have a large positive minus a tiny, tiny number. So this is going to be positive over here. So this tells me, what is cost doing? Cost then is decreasing until it gets to R is 2 and then increases forever after that. So yes, this is not only a relative min, but it's an absolute min as well, because this is the only minimum in the whole problem, okay? So I can say, well, let's see what we're trying to find. Find the dimensions. The dimensions here for part A, R would be 2, and H would be, where did I find H over here? I found H right up here. So if I put 2 in for R, I'm going to have 24 pi divided by pi times 4. So H would be 6. And in part B, the cost would be, and I would just put 2 and 6 in for this equation here. So the cost would be 0.15 times pi times 4 plus 0.05 times 2 pi times 2 times 6. And I would just say stop right there. If it's an FRQ, you guys get into the habit of safe stopping, okay? Safe stop is anything that you can put into your calculator and get any numbers that you can put into a calculator. Another safe stop spot is that. That's a safe stop spot. You don't have to know what that is if it's an FRQ, okay? Unless there's some other thing going on and you need to know what the value is, okay? So these are safe stop spots. Let's get into the habit of using that. So this is a nice little problem, you guys. That's a nice little problem. Do you know what I mean when I say that's a nice little problem? That means it might look familiar on Thursday. If you're taking that version, there are 2 versions. But if you're taking that version, it might look familiar to you. Okay. All right. Took a little time, huh? Took a little time. Okay, what else, you guys? That was a nice one. Whoever picked that, that was a good one to do. Okay, what else?
Can we do number 9?
Absolutely. Another good one. Okay. All right. Let's see. Find the dimensions of the largest rectangle that can be inscribed in a semicircle of radius 3 units. Okay. So I'm going to begin by drawing a semicircle. And the semicircle is going to have radius 3 units. Okay. And we want to inscribe a rectangle in here. And that rectangle could look like that. If it could also look like this, right? It could look like this. It could look like that. So there are lots of rectangles that could be inscribed. We want to find the one, the dimensions of the one that it makes it the largest. Well, what do they mean the largest? What do they mean when they say the largest?
Greatest area?
The greatest area. So by largest, they mean the greatest area. So we want to maximize the area of a rectangle. So remember I said, always start with, you're getting an equation for what you want to maximize or minimize. So we want to maximize the area of a rectangle. Well, I know the area of a rectangle. That's just length times width. Okay? I don't know why I put a period there, but it's just length times width. So I need to know what the length is and what the width is. So I am going to make this something that I can work with, and this is something that I would know to do just out of practice, you guys. So I don't know if I would necessarily expect this of you right now, but putting this on the coordinate axis, that's going to be helpful for us, okay? It's going to be helpful because then we can think, okay, well, I'm going to call this little piece here x, which would mean my length is 2x, right? So I'm going to be having 2x for the length. And now I want an expression for y, my height of the rectangle, or the width of the height of the rectangle. And to do that, I need to describe this point right here. I need to describe it. And here's where I'm using the semicircle, because this point is on this circle, right? Specifically the positive half of that circle. So what is the equation of a circle with radius 3 units? What's the equation of a circle with radius 3? Anybody remember? Back from, I know you did it in pre-cal, maybe in algebra 2, they used to, but I don't know if they do it anymore. A circle?
X squared plus y squared equals radius squared, right?
Very good. X squared plus y squared equals radius squared. And that's when we're centered at the origin. I could have centered this anywhere I wanted, but definitely at the origin is going to make it the easiest for me, okay? So now we need to solve this guy for y. So I'm going to subtract x squared, and then we're taking the square root. It would be positive or negative. We want the top half. So I'm just going to keep the positive. Okay. So my width is going to be the square root of 9 minus x squared. So now we have our area equation with only one variable. And that's what you always want. You always want whatever you're trying to optimize, you want to have it only with one variable. Okay? All right. So do I know anything about the graph of this? It looks like it might be fairly parabolic, maybe. I don't know. We'll see. We may have to consider that at the end. Okay, so I'm going to take the derivative and set it equal to 0. So to take this derivative, I'm going to have to use the product rule because I see a product of two functions of x here. So the derivative of 2x is 2. Leave your 9 minus x squared. And now I'm going to leave the 2x alone and multiply by the derivative of the square root of 9 minus x squared. So again, thought bubble, I'm thinking of that as 9 minus x squared to the 1/2, right? So chain rule time. 1/2, 9 minus x squared to the negative 1/2, and then times the derivative of the inside, which is negative 2x. That's what we're going to set equal to 0. And simplify. So let's clean this guy up. Let's see. I see a 1/2 here that I can cancel with one of these 2's, but I'm still going to have another negative 2 here. So I'm going to have a minus. That's going to be 2x squared on top, and then this is going to go to the bottom, and it'll be a square root. Okay. So now we have this expression, this equation to solve for x. So now it becomes algebra, solving this for x. So again, I'm going to multiply both sides by something that'll be helpful. I'm going to multiply both sides by that denominator. So multiplying by square root 9 minus x squared. When I multiply this together, I have 2 times just 9 minus x squared. So I've lost my square root, which is good. And when I multiply this by it, I just have minus 2x squared. And when I multiply this, I just get 0. So all of a sudden it got super nice. So I have 18 minus 2x squared minus 2x squared is equal to 0. And so that's negative 4x squared. I'm going to take the 18 over. X squared is 18 over 4, which is 9 over 2. So x will be plus or minus 3 over square root of 2. Okay. So I could do the same number line here, you guys, thing that I did before, where the smallest x can be a 0. And if I'm only looking at this piece here, the smallest x could be would be 0. And then I could do that sign chart. So let's see, if we put in something, let's go bigger. Let's go, the most x could be would be 3. So how about if we put in something like, let's put in a teeny tiny number close to 0. Close to 0. If we do that, where am I going to go here? I'm going to go right here. This will be the most cleaned up spot before yeah, I could go here. I guess I could go here. If I put in a teeny tiny number for x, this is going to be 18 minus a tiny number, so that's going to be positive. And so, and then it came from a single factor, so it'll switch signs. So this is a max, so that checks out. And so they want the dimensions. I found the x coordinates, and now I want the y coordinate. So y would be the square root of 9 minus this squared, which is back to the 9/2. So I would put that right here. Okay. So that was a long problem. That was a good one to ask about too. That's one that I do almost every year. / every year with kids because they have questions on it. So that's a good one. It's a good one, but you don't need to start it. Okay, what else? I will say that I like number 10. I'm looking at that. Do you want to do number 10? Is that a good one to do? A manufacturer wants to design an open box having a square base. Let's draw this. An open box having a square base. So once again, it's open. Square base. So I'm going to call my base lengths x and x. Don't know what y is. Don't know what the height is. It has a surface area of 108 square inches, and we want to find the dimensions that will produce a box with maximum volume. So always cue into what am I trying to find the maximum of? Trying to find the maximum volume. That's where you should start. I want an equation for volume. Volume of a box. Did I do this one with you guys already? I feel like this is familiar. Anyway, the volume of a box is length times width times height, right? So x times the height. All right. So again, I have two variables here. I want only one variable. I'm going to use the 108 surface area to change y to be x's. Okay. So I'm going to come off to the side and do that. I'm not sure where to go. I usually try to go underneath this box, but I don't know if there's room. I will try. So let's see. I know the surface area is 108. So I'm going to say that 108 is equal to, okay, I need the surface area. So let's go to the bottom of the box. There's the bottom. What's that area? X squared. And there would be one on top if the box was closed, but it's not closed, it's open. So there's just one x squared side. Plus, now let's go to the sides. So the area of that side is length times width, so x times y. And we have 4 of those, right? So there's going to be 4x times y. I can solve that for y and get my equation to replace this y with. So y will be 108 minus x squared all over 4x. Okay, sorry that I scrunched that in there, but that's what that is. So the volume will be x squared times 108 minus x squared all over 4x. So that's good because it's only one variable, and it's bad because it's a mess. So we're going to clean it up before you take the derivative. Clean it up, okay? So let's clean it up. I'm going to cancel one of these x's with that x on the bottom, and I'm going to bring out this 4 as a 1/4. So that's going to be 1/4 x times 108 minus x squared. That's a lot better. It would be even better if I could use the power rule though, when I'm about to take the derivative. So instead of using you can use the product rule here and that would work fine. But I'm going to go ahead and simplify it a little bit more. Not simplified, but go ahead and distribute that 1/4 x through. So 1/4 of 1008 or 108 is 27. So I have 27x minus 1/4 x cubed. Okay. So that's one I kind of do know the shape of. It's a negative cubic. So the shape of that is going to look like this. Okay. So when I take the derivative and set it equal to 0, I'm going to be finding these two spots, right? The derivative set equal to 0 will find me those two spots. So I need to keep that in mind that when I do the derivative equal to 0, that's what I'm finding. So I'm setting this equal to 0. Okay. I'm going to multiply both sides by 4. Oh, no, I didn't take the derivative yet. Goodness. Don't do that yet. Take the derivative. That's what we're setting equal to 0. So the derivative is 27 minus 3/4 x squared. That's what we're setting equal to 0. Solving it for x, I'm going to move the 27 over, and then I'm going to multiply both sides by 4/3. Negative 4/3, but it'll be all positive at the end because the 27 was negative when we took it over. So that's reduces to 9. 9 times 4 is 36. So x will be the square root of 36, which is 6. Plus or minus, but we can't have negatives in this situation. So x here is 6. And, but remember, it was plus or minus 6, which means over here with my little drawing, this was x equals negative 6. This is x equals 6. 0 is going to be somewhere in between there, right? Which is my minimum possible x. So this 6 is going to yield the absolute maximum volume, okay? If you don't like doing it that way, do a little number line to make sure that you got it right, but it's going to work out fine, okay? All right, so we want the dimensions. So x is 6 and we want y. So I'm coming over here to my y expression. Y is going to be 108 minus 6 squared all over 4 times 6. And you can say stop with an FOQ. So I would just stop there. Okay. So that's kind of a nice one if you have the other version of the text. So that's a nice one to start. All right, take a look and let me know if there's anything else on optimization you'd like to do before we go to the motion stuff. I do like these first couple. I like those as well. You want me to do one of those or a couple of those? Or are those just too easy? Hopefully they're too easy for you, but I'm happy to do those if you like. Anybody want me to? Anybody? Okay, I got a yeah, so I'm gonna do, let's do number 2 here. It looks a little bit more difficult than number 1. So we're finding 2 positive numbers such that the sum of the first and twice the second is 100. So let's change this to a math equation, okay? The sum, so we're adding 2 things. The sum of the first number, I'll call that x, and twice the second number, I'll call that y, is always equals in math, 100. On the test a couple of, I think it was unit 2, in one of the problems it said that the radius is twice the height, something like that, or maybe it was 3 times the height, I forget. There was something given to you like that. And I had a lot of students that wrote 2r is equal to h for that, okay? When you're translating an English sentence into a math sentence, it's going to, the is always equals. So if the radius is the only thing on that side, it's going to be r equals. And then twice the height would be 2h, okay? So be careful making your equations. All right, And then it says we want their product to be a maximum. So that's where you start. You start with what you're trying to maximize or minimize. So we're trying to maximize the product. I'm going to write an equation for the product, and I think I'm going to call it P for product. You can call it whatever you want. I'm going to call it P for product. And the product of two numbers is just X times Y. So that's the equation we're trying to maximize. We need to get either all X's or all Y's, and it truly doesn't matter. We're going to use this equation, solve it for either X or Y, and put it in for the other. I like to solve, I like to have X's in my equation. So if it's easy, I'm going to solve it for Y. So I am going to solve this for Y, but you would get the same answer if you solved it for X. You would just be getting Y first instead of X first. So we're going to have 2Y is equal to 100 minus X. So Y, if we multiply both sides by a half, Y would be 50 minus 1/2 X. So over here in my product equation, P will equal X times 50 minus 1/2 X. So multiplying that out, I'll get 50X minus 1/2 X squared. Okay. I know what that looks like too. It's an upside down parabola. That's an upside down parabola, and it has a maximum. It has a maximum when the slope is 0. So when we take the derivative and set it equal to 0, solve it for X, we're going to get the X value of the maximum. So taking the derivative, 50 minus the derivative here is just going to be X, right? Or negative X. Set that equal to 0. And that's an easy one to solve for X. X is just 50. And we want the two positive numbers. So Y will be 50 minus 1/2 times 50, which would be 25. But we could say stop there. Okay. I can see this being a multiple choice question. I think that's where I've seen it on AP. Okay. All right. For number 5, we have a rectangular enclosure using a wall as one side. And we have 120 meters of fencing to enclose the other 3 sides. So let's draw a picture. There's our wall. Here's our fence. And it's a rectangular enclosure. So it's a rectangle. Okay. I'm going to call this X and this Y. And we want to know what are the dimensions that will yield the greatest area of the rectangle. So the area will be X times Y. And once again, we want to make it all X's or all Y's. So I have 120 meters of fencing to make this. So I'm going to have 2Y plus X is 120. And again, I'm going to solve it for Y. I know that it's really easy to solve for X, and you can if you want to. I'm going to solve it for Y though. I'm going to have Y is 120 minus X all divided by 2. So that's going to be 60 minus 1/2 X. So the area will be X times 60 minus 1/2 X, which is 60X minus 1/2 X squared. There's our upside down parabola again, which has its maximum when the slope is 0. So take the derivative, set it equal to 0. Easy to solve for X. And then we get the Y value. So our dimensions will be 60 by 30 meters. So those are nice kind of quick little multiple choice questions. Okay. All right. Anything else on optimization before we go to motion? Anything else? All right. So I'm really not sure what to do here. I don't know if you'd like to go to worksheet 4. I can do worksheet 4, or I can do that extra thing. I made up a little extra FRQs worksheet. You're not going to have to turn it in, but if you want extra practice with FRQs, I did a little extra this morning. I'm in the process of making your test, and so I was looking for a good FRQ, and I found so many. It was like, I thought, oh, I'll just make them some extras, and then they can have them if they want them. So I put the solutions in my solutions folder in Schoology. So if you want to practice more, you can. But I'm not sure what you would rather do. Would you rather do from worksheet 4, or do you want to kind of keep that for homework and do that on your own? Up to you guys. I would like to do an FRQ though. So either 16 or 17, or one from your extra ones. Somebody say something, because I'm not sure. In class you would say something, I know it.
I like number 16 on the worksheet 4.
I will go with that. Number 16 on worksheet 4. Okay. So on this one, we're not going to use a calculator. Okay. So on this one, they give us, well, we're on the x-axis and time is greater than 0, and they give us the position. So we have the position function. Okay, on what intervals is the particle moving to the right? So we know that the particle moves to the right when the velocity is positive, and that's just something I need you to know. Okay, that will be our justification. Okay, so I want the velocity to be 0. So first I need to find the velocity. I want the velocity to be positive. So I need to do a sign chart on velocity. So first I need to find velocity, and velocity is always the derivative of, they called it x here, the derivative of position, right? So I need to say that. So that's what, for full credit, you have to write that, okay? So, and now we're just going to use the power rule. Like that. I'm going to set this guy equal to 0 because I need the sign chart. So there's a 3 in everything. Since it's a positive 3 in everything, I'm going to go ahead and divide it out. It's not going to change the signs of my answer. So I'm dividing out everything by 3. And remember, you guys, don't divide by a negative, because then your signs are going to be all backwards. So you can divide by a positive though. That's nothing wrong with that. And then we have factor time, t and t, 4 and 2, and they both need to be negative. So t is 2 and 4. Sign chart time, we're starting at 0. I put 2 and 4 on my sign chart, and I'm doing a sign chart for velocity. If I put 1 in for time, I'm going to have a negative times a negative, and that's a positive. And since both of these came from odd powered factors, I know I'm going to change the signs each time. So
Miss
here,
Marie?
yes.
If you did have a negative, like if it was negative 3t squared, could you still factor it out and just not divide it?
Exactly. I would have left it like out here.
Okay.
Yeah. Absolutely. And you can always do that, right? But yeah, if we're just looking at the signs, then this will work. Okay, so on this piece, we're moving to the right. On this piece, we're moving to the left, and then we're going to move to the right afterwards. So the particle is moving to the right on 0 to 2 and greater than 4. Or you can say 4 to infinity. And you're welcome to use the interval notation, or you can use the inequality notation, whichever you prefer. Or you could write it out all in English, and that's fine too. And I'm going to say since V is positive there. That's my justification. Okay. Next up, part B, on what intervals is the particle speeding up? So again, when you see particle speeding up, I need you to be thinking velocity and acceleration have the same sign. So I need you to be thinking A and V have the same sign. That's going to be our justification. So I have the signs for velocity. Now I need to get the signs for acceleration. So I need to go find acceleration first. Acceleration, I need to say, is the derivative of velocity. So I'm taking the derivative of velocity here, 6t minus 18. Set that equal to 0. T is equal to 3, okay? And now I'm going to make a sign chart, and my sign chart will have, I want it for both acceleration and velocity because I need to know where they have the same sign. So I'm going to use the 2 and the 4 that made velocity 0, and I'm going to use the 3 that made the acceleration 0. So 2 and the 4, that made the velocity 0, and the 3 makes the acceleration 0. I'm going to put that up there just to remind myself that that's where that came from, acceleration, and the 2 and the 4 came from velocity. Okay, we already found the sign chart for velocity, so I'm just going to copy that down. So positive 0 to 2, negative 2 to 3, and 3 to 4, and then positive after 4. For acceleration, if I put a number here in, like a 1, I'm going to get a negative. So negative, negative, and then it's going to change signs, positive, positive. And now I look, I want the two signs to be the same. They're both positive from 2 to 3 and after 4. So that's going to be my answer. So the particle is speeding up. On 2 to 3 and greater than 4, since acceleration and velocity have the same sign. Oops, same sign. Okay. Speed at time 3. Speed at time 3. Well, again, I need you to know this. So speed at a time, speed, I need you to know speed is the absolute value of velocity. Speed is the absolute value of velocity, always. So all I need to do is find the velocity at time 3 and take the absolute value of it. So velocity at time 3, I think I'm going to come and I guess since I did take a 3 out, I would come down here. I would have to remember though, if I came down here and put 3 in here, I would have to remember I had taken that 3 out, right? So it's safe to go up here. I can come here multiply that by 3. So that'll be 3 times -1 times 1. So that's a -3. So the speed at time 3 is 3. Okay. All right, lastly, what is the total distance traveled by the particle? Total distance traveled by the particle from 0 to 3. Okay, so I'm going to the right till time 2, and then I'm going to the left. So if I was writing if I made a little diagram, I'm starting going to the right till I get to time 2. There's my little diagram. Then at time 2, I turn and go to the left until I get to time 3. I need to know what my position is at these places. Okay? If I know my positions, I can do my total distance, right? So my position is going to be S at 0 for that. It's going to be S at 2 for that, and S at 3 for that, right? So my total distance will be this distance, which is, if you want, I'm going to use absolute values, but if I use absolute values, it doesn't matter what comes first. You don't have to use absolute values if you put S of 2 first, though. Does that make sense? Because S of 2 is going to be bigger than S of 0, because we went to the right. That's where this diagram is very helpful. Okay, so if you use absolute values, it doesn't matter which comes first, 0 or 2. But without the absolute values, you just put the S of 2 first. Okay, and then we're going to add the distance from time 2 to time 3. And again, here, the time 2 should come first if we don't have absolute values. But with the absolute values, it doesn't matter. It'll all take care of itself. So a little diagram is helpful there. S of 0, I'm putting 0 in for, and I said S, but I forgot that they called it X here, so I guess it should be X's, but whatever. I'm going to know what you're talking about there. So X at 0, let's come off to the side. X at 0 is just that -1. I need X of 2, and X of 2, let's see if we can do this, you guys. So we'll have 8 minus 9 times 4 is 36, plus 24 times 2 is 48, minus 1. You know, we could safe stop here too, FYI, but anyway. This is 56 minus 36 is 20, minus 1 is 19. I think that's 19, maybe, hopefully. And now we need X of 3. For X of 3, we're going to have 27 minus 9 times 9 is 81. 24 times 3, 12 plus 1 is 72, minus 1. Let's see, this is going to be a -9, -10, plus 27 is going to be 17, hopefully, maybe. And then we put all those in. And this is a safe stop spot. Another safe stop spot would be it would be long, but we could just put the 2 and the 3 here and not simplify it, and that's fine as well. It would just be long, but that would work. do we remember, what's the displacement, you guys? The displacement from 0 to 3. How do you do that? Displacement.
Isn't it the distance formula? Or am I mistaken?
It's easier than that.
That's
Displacement is just the position, your ending position minus your starting position. Ending
Oh, got
position minus starting position. That's displacement. If you're on a straight line, okay, this is a straight line. You might be thinking of physics where you're on curves. We'll do that later on, but for right now, this is just a straight line, so it's just the last minus the start. So x of 3 was our 17, x of 0 was -1, so the displacement here would be 18. Okay. All right. So that was a little longer than what we would have done in class. I probably wouldn't have done all those optimizations with you, but that's pretty much what we would have done in class. So if there is anything else that you'd like to do, I'm here and I'm not doing a whole lot. So if there's anything, any other questions that you'd like? Anybody else have any questions? How are we feeling about everything? Yes or no? We okay? All right. I have some thumbs up. I'll take that. Okay. Well, I will be back at 3 o'clock if you want to come back and ask any questions, or you can just ask now. It doesn't matter. But I'll be back at 3 o'clock regardless.
Just to clarify, on the last problem, was the safe stop when you had the absolute value bars and like x parentheses 3 and all that?
Yeah, let me clarify that. So a safe stop, this with the x's, it's not a safe stop yet. You have to go to this point to safe stop. Okay. Good question though. Yeah. I think of it as this I can put into my calculator. This my calculator would have to know what x was, you know, and that wouldn't be a safe stop spot. Okay. All right, guys. What else? Anything else? Okay. I'm so happy so many of you came, and I'll be back about 3 o'clock. Okay. All right. See you guys.
Thank you.
Thank you. Thank